Okay, here we go with chapter 2. Now, this chapter is all about how we organize a data set, right? So, the whole point of this process is to learn some simple tables and how to create figures that can help us get a good idea of what our data looks like. There's a section in the textbook in the reading about interpolation, and we're not going to be going over that in this class. Okay, so this is the data that I collected at the beginning of the class, right? This is the how stressed out do you expect to be when taking stats this semester. And as you can see, we have some scores here that sort of the question was between 0 and 100, 0 being not stressed at all, 100 being sort of maximally stressed. And if we just sort of peek through the data here, it looks like the lowest score is 50, right? So there's a few of those, at least 4 of them that I see right out the gate. Looks like we've got 100, right? But we don't have anything too terribly low. And this isn't the biggest data set, right? Typically online classes tend to be a little bit smaller. Sometimes when I teach these classes in person, I might have 60 to 80 data points, that range anywhere from as low as 3 to as high as 100. So it's a little bit tough to sort of compare these data with other classes, but typically the gist of sort of what students report is about the same. So, even with a small data set like this, the first thing we sort of ask ourselves as researchers after we've collected the data, the very first thing we want to do is figure out some sort of way of organizing it in some manner that it makes sense to us. And one of the ways that we can do this is by creating tables or graphs that we broadly refer to as frequency distributions. And so frequency distributions are one of the more common ways that we can organize a data set, right? Using this technique, it allows us to take a quick look at the data, just sort of see the general picture of the data, right? It gives us an idea without doing any sort of mathematical operations or any statistical analyses. How did most people respond, right? What is the shape of the data? And so a frequency distribution, it's going to allow us to see exactly how many people expect a stress level of 100, 99, 98, right? All the way down to 0, right? So we'll start with a simple one, right? So here we've got 12 scores on some sort of hypothetical 15-point quiz, right? Now, one of the things you can do is just sort of eyeball this data, right? How many people scored a 13? Well, it looks like one person got a 13. Okay. What's the most common score? Well, one of the things we can do is sort of go through all the scores and kind of count them. It looks like 10 sort of jumps out, right? How many 10s do we have? 1, 2, 3, 4 of them, right? I think that's the most common score. But anyways, you can see with even a small data set like this, right? Just 12 scores on a 15-point quiz. This is a fairly labor-intensive exercise, right? Imagine trying to do this with a really large data set. So to make things easier on ourselves, what we can do is group these scores into a frequency distribution table. And so this will help us visualize the data a little bit easier. And so as you can see here, I'm just making a table, and this is just a very basic one. I'm starting off with one column for X and one column for F, right? And X is the column where we're going to record the actual values, right? So we start with the largest of all possible values. Here it looks like it's 15. And we would work our way all the way down, right? We could go down to 0. It looks like 7 is the lowest score, so I think we'll just be content to go all the way down to 7. And F is the column where we're going to record the frequency of each occurrence of X, right? So how many instances of 15 occur, right? So I put 15 in here in the X column, and I'd count how many times 15 occurred. So 1, 2, and I'd mark 2 under the frequency column. So that means the score of 15, right? The score of 15 occurred twice in this data set. Then I'd go down to 14. I'd record how many times 14 occurred. 13, I'd record how many times 13 occurred. Go ahead and pause the video and give that a shot. Try and make, finish out this frequency distribution table. And on the next slide, I'll show you the one that I've created. So this is what you should have got, right? If we go ahead and transcribe all of these x values and tabulate the frequency of every occurrence, we get every value in the data set. And note that each x, right, each score here corresponds to a specific frequency value, right, which denotes the number of times that it occurred, right? So again, 2 people got a 15, 0 people got a 14, 1 person got a 13, right? You can see it right there. Nobody got a 12. It looks like there's 2 11s in here. There's one. There's another, and so on, right? So that's one way that's the way to create a very simple frequency distribution table, and it's fairly easy to do with a limited number of scores. And that's useful information for us, right? There's mathematical operations, some basic mathematical operations we can do from that table that we'll get to in a moment. But in addition to just simply displaying the frequencies of specific scores, there might be other pieces of information that I want to add to the frequency distribution table that I might find useful. So for example, we can add proportions, right? So a proportion is measured with the fraction of the total group associated with each score, right? And the formula for finding a proportion is quite easy, right? It's to divide the frequency of a score, right? The number of times it occurred by the total number of scores. So remember, 4 people got a 10 on our quiz, right? And we had a total of 12 scores. So we would divide 4, right? 4 is the number of times people got a 10. We would divide that by 12 in order to find the proportion of people who scored a 10 on an exam. And if you do that in your calculator, I'll go ahead and do it right now as well, right? So if I would divide 4 by 12, I get a proportion of 0.33333. It sort of goes on and on and on. What you want to do is report proportions out to 4 decimal places. So the proportion of people that got a 10 is 0.3333, right? Proportions are very valuable when we're doing math, right? We're going to do proportions, work with proportions a lot in this class. But when we actually describe data, we don't tend to do it in terms of proportions. Typically, we most often talk about data in terms of percentages. And so percentages are simply relative frequencies, right? 15% of students received an A, 38% of students received a B, and so on and so forth. So in order to calculate a percent, you can compute the frequency, right, divided by the number of scores, just like we did, and then multiply that by 100. So in other words, you can take the proportion that you've computed, multiply that by 100, and it will give you the percentage of people that had that particular score, right? Now, it should be fairly intuitive to you that you can also simply move the decimal place of a proportion 2 places to the right in order to find a percent. So we had a proportion of 0.3333, right, of the proportion of people that got a 10 on that quiz. We can very easily convert that to a percent by moving the decimal place 2 places over to the right, and that would give us 33.33%, right? Okay. So in the case of our data, right, converting a proportion to a percent allows us to say 33.33% of students who took the quiz got a 10. It's a little bit more intuitive, right, when it comes to describing data than saying, the proportion of people that got a 10 was 0.3333, right? It's a little bit sort of easier for people to understand. Okay, so as you can see here, I've added these 2 new columns, right? One is for proportion, and one is for percent, right? What I want you to do before you move on to the next slide is simply compute the proportion of people who got a 7, an 8, a 9, and so on, all the way up to 15, and fill them out in your table. Remember, report that out to 4 decimal places. And then I want you to do the same thing for percentages, right? So remember, you can multiply what you get in proportions times 100 to get the percent, or you can simply move the decimal place 2 places over to the right. So go ahead and pause the video and try and figure out the proportions on your own here. And here's everything filled in, right? So if we want to figure out the proportion of people that got a 7 on the quiz, we would take this 2, right? 2 people got a 7 on a quiz. We divide that by our total number of scores, which is 12. And that's going to give us a proportion of 0.1666666, so on and so forth, right? But when you're rounding it up to 4 decimal places, you just round that last place up, right? So you'd end up getting 0.1667. Nobody got an 8, right? So that's very easy. That's 0. One person got a 9, so 1 divided by 12 is going to give us a proportion of 0.0833. And so on, right? You do that all the way up to the top of the table here. Oh, it looks like I have a little bit of a mistake here. Let me fix that. You do that all the way up to the top of the table until you're complete. And then in order to convert all of these to percentages, again, you simply move the decimal place 2 places to the right. I've chosen to just round to 1 decimal place. If you rounded to 2 decimal places, that's fine as well. You're not going to really get much of a different answer. But if we convert a proportion of 0.1667 to a percent, rounding to 1 decimal place, we get a percentage of 16.7, right? Again, nobody got an 8. 8.3% of the people who took our quiz got a 9. 33.3% of people who took our quiz got a 10, and so on, right? So in addition to giving you sort of the frequency distribution, giving you an overall idea of the shape of the data, you can get a sense that you can compute proportions, which you can use to do math at a later stage, and you can compute percents, which helps you describe the data in more intuitive, sort of easy to understand terms beyond proportions. And once you've computed these percents, right, you can use these percents to describe things like percentile rank or percentile, right? So a percentile rank is a proportion of scores in a distribution that any one specific score is less than or equal to. So for instance, if you received a 95 on a statistics test, and that score was as good or better than 88% of the students that are taking the test, that means your percentile rank would be 88. And you would be in the 88th percentile, right? A percentile is the point in the distribution at or below which a given percentage of scores is found. So for example, the 28th percentile of a distribution of scores is the point at which or below 28% of the scores fall. And this is another concept that we'll be working with sort of in the kind of middle-ish of the semester when we first start learning some statistical analyses. We'll be really interested in sort of where maybe an individual score or a group of scores may fall in relation to the performance of an entire distribution, right? So that's something that we'll be interested in exploring. And the way you can use that in your tables by calculating what we call a cumulative percent, right? So what you want to do is you want to start with the percentage value for your most lowest X score, right? And you start with that value, right? So we could take the 16.7 and we can put it in this new column that we're calling C percent, meaning cumulative percent. So we put 16.7 here. And what we're saying, right, is that anybody that got a 7 or lower scored in the 16.7 percentile, right? Or a percentile rank of 16.7. And what you're going to want to do is continue to add a value to this cumulative percent going all the way up. And up at the top, you should get really close to, depending upon sort of the rounding that's going on here, you should get very close to 100. So what you're doing is taking this base value that you have in your current cell and adding the percent, right, from the value above that. So if we started with 16.7, if we want to figure out what the cumulative percentage is for somebody that got an 8, well, we'd add 16.7 to 0 because there was 0% of people that got an 8. So we'd end up with still getting 16.7 here. But if we wanted to find the cumulative percentage of people who got a 9 or lower, we could take that 16.7 that goes here and add it to 8.3. And what would that be? Let me just figure that out on my calculator really quickly. 16.7 plus 8.3, that's going to give us 25, right? So we put 25 here. And we'd say anybody that got a 9, right, at least a 9 or lower, right, scored in the 25th percentile, for example. So what I want you to do is finish filling out this cumulative percent column. Go ahead and pause the video. When you come back to the next slide, I'll have it all figured out for you. And so here it is, right? So again, this is kind of where we left off, right? We started with 16.7 because that's the percent for the lowest possible x value that we have in our distribution, and we just continually add to this sort of a running total, the percent from the row right above it, right? So 16.7 plus 0 is 16.7. 16.7 plus 8.3 is 25. 25 plus 33.3 is 58.3, and so on, all the way up until we get to 100. So try and answer this question. Imagine we have a student that took this exam or this quiz. Her name is Sam. Sam scored a 13. Sam got a 13 on the exam. What is Sam's percentile rank or Sam's percentile? Well, a score of 13, right, corresponds with a cumulative percentage of 83.3, right? So Sam scored in the 83.3 percentile, the 83rd percentile, or her percentile rank was 83.3. How about somebody that got a 10 on the quiz? Well, we can find 10 right here. We could go over to the cumulative percent, and that person was in the 58.3rd percentile, or probably to make it easier, just say 58th percentile. Or you could say their percentile rank was 58.3, right? So basically, 58.3% of students who took this quiz got a 10 or lower, right? So it's hard to see here, but Sam's quiz score has a percentile rank of 83. He scored an 83rd percentile, right? I should say too that these sort of tables only work for our data, right? They don't give us any predictable ability, right? So if we gave this quiz to a whole totally different set of students, right? Another 12 different students, they might have a different frequency distribution, right? And so their cumulative percentages and proportions may change. So we can't use these to make a prediction, right? We wouldn't predict based on these data that 83.3% of all students who take our quiz should get at least a 13, right? Because this just pertains to one specific set of people, a sample, if you will, that took our quiz. Okay. Well, let's ask this question, right? We have these stress scores. We don't have too many of them, like I said, compared to other classes, but there's a few, right? And we could ask, well, would a frequency distribution table help us make sense of our stress scores, right? Well, I made the liberty of making one, right? So, here we have our lowest value up to our highest value, and I'm filling in the number of specific occurrences, right? So 5 people got a 50, 1 person got a 55, 2 got a 60, and so on. Okay, well, even with a small data set like what we have, I think that a frequency distribution table like this is still a bit long, still a bit cumbersome. In this case, what we want to do is use something a little bit different. What we want to use is something that we call a grouped frequency distribution table. So when you have a wide range of scores like we do, the idea is that we want to put some of these scores into groups, right? We want to create groups, ranges of values in which multiple values can fit into, right? So we're putting each raw score, right? We're tabulating how many times raw scores occur within a specific range of values that we call class intervals, or you'll sometimes hear me refer to them as sales or bins as well. It's sort of an interchangeable idea, right? So what we're going to do is instead of tabulating every individual occurrence, we might say, okay, we're interested in every occurrence, every time a value occurs between 0 and 9. And maybe we're interested every time a value occurs between 10 and 19, and 20 and 29, and 30, and so on, right? All the way up to, say, between 100 and 109. We count how many times that occurs. So you're going to need to make a table like this in the homework assignment, of course, which shouldn't be surprising. And in the homework assignment, I set some pretty clear parameters. If I recall correctly, I think I want you to make a table that has 7 distinct class intervals, and I think I want you to make a table where the range of the widths is only 5, right? But you'll see it on the homework. I think I'm giving you a bunch of data from a speed camera, for example, and I think you have to turn that into a frequency distribution table. But you might find some scenarios, right? For those of you that are very interested in psychology, pursuing psychology as a science, and you're interested in working in a laboratory environment, you might find yourself in a scenario where you have to make one of these tables from scratch. So here's some general guidelines or rules that you need to take into consideration when making tables like these. The first thing is you want to create anywhere between 5 and 15 of these class intervals or bins or cells, if you will, right? And you want all of the intervals to be equal width. I find on average, depending upon the range of your scores, a lot of times 10 class intervals of equal width works pretty well. But if 8 will work, if it makes it easier to visualize the data, that's fine. That's no problem, right? In our case, we have scores that range between 0 and 100, right? So 11 classes will actually work pretty fine for our data. So here we want to have 11 class intervals. What do you think our width should be? Well, I kind of gave it away, didn't I? Yeah. Our width should be 10, right? But I'll get to that in a second. One thing's for sure is that your width, right, the width of each interval should always be a simple number. And again, it depends on the data. Like I said in the homework, I'm forcing you to do it. Each interval is a width of 5. But again, it could be 2, 5, 10, 20. Whatever it is, it should be a fairly simple number. And the width needs to be the same, right? Note number 1. The width needs to be the same for every single bin or class interval that you create. Your intervals should always start with a multiple of the width, right? So I told you that we're going to go ahead and do 11 class intervals for this stress data, and we're going to use a bin width of 10, right? 10. So I want each class interval, the first value of each range, right, to be a value that is perfectly divisible, meaning that there's no remainder, perfectly divisible by 10. Okay, we're going to start with 0, right? 0 to 9. 0 doesn't count, right? But 10 to 19 could be my second bin. And the width of our bins is 10, right? So is 10 divided by 10 without any remainder? The answer to that question is yes. Maybe our second bin, right, we're keeping with this width of 10, would be 20, right? It start at 20 and go to 29. Is 20 divisible perfectly by 10? It is, right? Our next bin would start with 30, then 40 and 50 and so on, right? So you want the very first value in the range of your class intervals or your bins to be perfectly divisible, right? Perfectly divisible by the width of your bin. So again, think about the homework here. I'm telling you that you have to have class intervals that are width of 5. So whatever you start each one of the values for your class interval, whatever you start that range with, then it needs to be divisible by 5 without any remainder. Keep that in mind. And then finally, the values in the very first column, right? The range of X values, your range of bins, need to start with your highest range and work all the way down to your lowest range, okay? So I went ahead and took the luxury of making a table that corresponds, right, a frequency distribution table that corresponds to what we just talked about, right? So note, this is a little bit of a difficult table. I could have made an editorial decision to maybe change this a bit, but I think that this is worth it because even though we didn't get any of these lower scores, there's still the possibility that we could have got them. And so it's a good idea, it's a good rule of thumb to make sure that that's represented in the table. But that's also a bit of a sort of editorial decision, right? I've just went ahead and decided to do that. So note here, right, well, first let me just talk about the X values here, right, as they relate to these guidelines. So remember, I say 5 to 15 class intervals with equal width. Well, here I decided to do 11, right? And they all have a width of 10, right? So 10 values fall into each and every one of these ranges. And it's the same for everyone. It's not, I don't have a width of 9 here and 11 here and 10 here and then 10 again. They're all a width of 10 in every single one of these bins. The width should be a simple number, right? I said 2, 5, 10, 20. Here I've decided to use 10, right? You wouldn't use 3, you wouldn't use 7, right? Those aren't easy, intuitive numbers to work with. And chances are, using weird values like that, your very first value here, number 3, is probably not going to be perfectly divisible by the width of your bin. Here my values are, right? I mean, 0 divided by 10, anything divided by 0 is going to produce a 0. So really what matters sort of is this bin right here. If we take the width of our bin 10, divide that by 10, right, we get 1. 10 divided by 20 will give us 2. 10 divided by 30, and so on. And then note the values in this first column and the X column start with the largest range and work their way down to the smallest range, not the reverse. So I'm not starting with 0 to 9, 10 to 19, 20 to 29. No, you start with the largest value range and work yourself down. And then all I did to fill out the frequency, right, is looked at our data and said, well, how many people had a stress rating between 50 and 59? And 6 people did. So I wrote that down. Yeah, it's pretty tough. 4 people fell between the range of 60 to 69. 1 person had a score between 70 and 79, and so on, right? So here I have it. All right, good. Now I want you to do a little bit of work, right? What I want you to do, go ahead, after I'm done talking here, after I give you the instructions, pause the video and do this yourself. But what I want you to do is calculate the proportions for all these ranges, right out to 4 decimal places. Calculate the percentage, and also calculate the cumulative frequency, right? Or I'm sorry, cumulative percentage. I do have cumulative frequency here. That works the same, except instead of doing it for percentage, you just do it for frequency scores, right? We didn't do that on a previous one, but that should be fairly self-explanatory. You should be able to figure it out. So again, go ahead and pause the video, compute the proportions, percents for each range, cumulative frequency, and cumulative percent. Okay, so before I give you show you the answer, I just want to review, because this is an important part of your homework assignment, and it could be an important part of your exam. So again, typically speaking, approximately 5 to 15 class intervals with an equal width being a simple number. Intervals should start with a multiple of the width, and the values in the first column should go from highest to lowest. And this is just a reminder of how to compute these different columns that we're talking about. So compute proportions, divide the score in each frequency bin by the total number of scores in the data set, and round that out to 4 decimal places. To find the percent, you can just multiply each frequency by 100, or simply move the decimal point of the proportion over 2 places to the right. To get the cumulative frequency, start with the frequency value of your lowest bin range, right? So in our case, it would be 0 to 9. And continue to add the frequency from the next highest bin, right? So you're going to get a running total starting from the lowest value that ends with the total number of people in your data set. And you're going to do essentially a similar thing with cumulative frequency, right? You're going to start with the percentage value in your lowest bin range. So again, 0 to 9. We had 0 people that got a stress score in 0 to 9, so we'd start with 0. And just keep adding the percentage value in the bin directly above the one that we're on, right? And get a cumulative percentage frequency all the way up to the very, very last bin, right? All the way up to the largest bin. So this is what you should have got. Fairly simple math, fairly simple, easy things to work with, right? Okay. Cool. Yeah, so now's the point where I would ask you if you have any questions. You should be able to construct and read and interpret a frequency distribution table. Remember, if you have any questions, just go ahead and ask one in the thread. Chances are, if you have a question, somebody else has the same exact question, right? Maybe they're just a little too shy to ask. Okay, so let's talk about graphs, or really sort of what we should be referring to as figures, right? Figures. They're visual representations of our data. They're meant to really give us an idea of the shape of a data. And so for one of the homework questions on this assignment, you're going to have to sketch a frequency distribution, right? So there's some things I want to make sure you understand. When you're dealing with continuous data, right, that's data that can take on a fractal value, right, meaning that we can get down to an incredible level of precision depending upon how precise our measurement tool is, right? So you can imagine I have a classroom of students. I can measure the height of every student in the room. And if I have a very crude measuring device that only really allows me to say anything about someone's height just in terms of feet, I say, well, this person's 5 feet, this person's 5 feet, this person's 6. But maybe I have a better ruler, right? Maybe I have a measuring tape that's a little bit more precise, and I can say, oh, well, this person's 5'2", and this person's 5'7", and this person's 6.3, and so on, right? If I have like a laser measuring device, which allows me to get a ridiculous degree of precision, I can report it out to an incredibly infinitesimal fractal value, and I can say somebody is 5'2", 3, 7, 6, 6, 5, 1, 8, right? You know, depending upon, again, how precise my measuring tool is. And so that's continuous data, right? There's fractal values that sort of run up to the border of the next value in the sequence. Whereas discrete data is indivisible, right? Discrete data is indivisible. So for example, the number of TVs that you have in your home, we would consider that discrete data. Why? Because maybe you have one TV, maybe you have two, maybe you have three. But what you don't have is 3.2 TVs, right? There's no such thing as 3.2 TVs. A TV is a singular individual object, or indivisible object. You know, if we have 25 students in a class, and you know, 2 people don't show up, you know, we wouldn't describe let's say I'm sorry, let me rephrase that. Let's say I take attendance every day for a week, right, over 5 days. And one day I have 22 people show up, and I have 24 the next day, and then 25, and so on, right? And I might take an average of that. And the average attendance for that week might be 22.3 people showed up. Well, I would actually round that, because it's discrete data. I would round that to a more reasonable value that really represents the data. And I would round 22.3 to 22, because I can't have a fraction of a person, right? People aren't fractal. The people are whole indivisible units. So I wouldn't report the average attendance as being 22.3. I report my average attendance as being 22, right? Okay, so my whole point of all that rant was that the type of figure, right, the type of graph that you make for your data depends upon whether or not your data is continuous or your data is discrete. If your data is continuous, there are 2 types of figures you can make to display your raw data. One is something we call a histogram, which is what I have here, and I'll explain it in a bit. And the other is called a polygon, which is on the next slide that I'll explain in a bit. If you have discrete data, then you would use a bar graph, which I'll talk about in a few slides. And don't be fooled. This is a histogram, right? You say, well, these are bars, aren't they, Prof? Yes, they are, but this is not a bar graph. This is a histogram. One of the things that separates it from a bar graph is all of the bars touch each other, right? In a true bar graph, there's separation between each one of these individual bars. In a histogram, all of the bars touch each other because this is all considered continuous data, right? Here we've got continuous data going from 30 all the way up to 45, right? So some things to note when you have to make a histogram. On your x-axis, which is this axis at the bottom here, going horizontally, that's going to be all of your scores. And under each one of these bars, you want to put the range of values if you're using a grouped frequency distribution table. So for example, we're building this histogram from these data right here that are taken from the book, right? And this is a small grouped frequency distribution, right? No different than what we made at this last step. Except here we have an interval width of 2, and we've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8 class intervals, right? So 2 people had a score between 30 and 31. 4 people had a score between 30 and 33. 3 people had a score between 34 and 35, and so on. So note at every bar, right, underneath every bar, the width of each interval fits in there perfectly. So note, 30 to 31 people, note that they got a 2. And on the y-axis here, that's where you're going to put your frequency, right? This is the number of times that the values occurred within these individual ranges, right? Here, 4 people had a value between 32 and 33. And as you see here on the table, that's correct. 3 people had a value between 34 and 35, okay? So again, bars are touching, right? If you're using intervals, an interval range, then each bar should have the interval range directly underneath it, right? Make sure that's articulated on the x-axis, and make sure that your y-axis is also denoted, which represents the number of times each one of these things occurred. And on the y-axis, you want to label it. You want to label it as frequencies, and you want to label whatever it is we're measuring on the x-axis. If we were making a histogram for here, for our stress data, right? Our x-axis would have something underneath that says something like stress scores. And we'd start with a bin of 0 to 9, 10 to 19, 20 to 9, and we'd just be marking, right, with all the bars touching, where those particular stress scores, the number of stress scores that occurred within that range. The other type of table that you can make for continuous data is a polygon, right? And this is an example of a polygon. And there's a few differences here. For one, the polygon is expressed as continuous data, even if it's binned, like you see it here, right? So we're starting with the lowest value, working our way up to the highest possible value. But one of the things I want you to make a note of is that the dots, right, that represent these frequency values are placed in between the ranges that are represented in the bin. So note here that 2 people had a score of 4 or 5, right? So we go to the frequency 2, right? We want to put a dot there, but don't put your dot over 4. Don't put your dot over 5. Instead, put your dot right in the middle, right, between 4 and 5. 3 people had between a 6 or a 7, right? So we'd go over to 3. Here we have 6 and we have 7. Again, don't put your dot over 6. Don't put your dot over 7. Put your dot right in the middle in between 6 and 7. And then what you want to do is connect all of these values by a line, right? By a straight line. And you want to start that line at some point before your first value, right? So it's going into your first value from the x-axis all the way up to that first value. And then you want to end from your last dot, right? From your last data point at the x-axis to a point just shortly beyond your final value, right? And that's all there is to that. That's all there is to a histogram or a polygon. And again, you do this for continuous data only. For discrete data, we make a bar graph, right? And all it is doing is showing, again, what's being measured on the x-axis and the frequency occurring on the y-axis. And this could be sort of clinical psychology data, perhaps, right? Where the number of people that have type A, type B, and type C personalities are simply tabulated, right? And in this case, 10 people had a type A personality. So A would be underneath that bar, and it would go up to 10. 5 people had a type B. 20 people had a type C. So again, note, the big difference between this and a histogram is the bars don't touch. And the reason why they don't touch is because this is discrete data. You can either be a type A personality, you can either be a type B, or you can be a type C, but you can't be both, you can't be all 3, right? It's an indivisible category that somebody that is diagnosed as one of these personality types falls into. So hopefully that idea makes sense. So again, you're going to be given a scenario on the homework. You're going to have to decide what you think is the best graph, the best figure to make. And you're going to have to do it based on these parameters. So here, it looks like my little table here is cut it off, but here I went ahead and took the liberty of making a histogram for our stress scores, right? So here's the bin of 0 to 9, which is a 0. 10 to 19, which is a 0. So note how the bins are positioned underneath each one of the, the values of the ranges are positioned perfectly underneath each one of these bins. And now we get a value, right? 6 people got a 50 to 59. So that's noted right there, right? Frequency of 6, 50 to 59, and so on. Looks like our 100 to 109 got a little bit cut off, right? But that's a nice little histogram for our stress scores. That works quite nicely. And again, this would be the appropriate way to describe our stress scores, right? Because this is continuous data, right? Continuous data that runs from 0, caps out at 100. We don't have any fractal values, but conceivably somebody could be, feel that their stress prediction might be 72.3, right? I mean, that's awfully precise, I suppose. But is it possible that could be a response? Surely it is, right? So that means that, a person can respond in a way in which the level of precision of their response can go beyond simply some sort of discrete whole number. But here's our data for eye color from this class. And I apologize, it's a bit of a dodgy sort of graph here, but I thought it was kind of funny because this is such a contrast. Anytime I've taught this class, we have a grand total of 3 different eye colors, right? You can see it quite well in the table here. One person reported having blue-green eyes. 2 people reported their eyes as being dark brown, and 17 people, right, reported their eyes as being brown. And so as you see here along the x-axis, we have these 3 categories, right? And along the y-axis, we have the frequencies. And where each one of these bars peak out correspond to the frequency distribution from our data, right? And again, right, somebody might choose to describe their eye color as blue-green, right? Okay, and that may be perfectly true. But if your eye color is blue-green, it's not brown and it's not dark brown. Similarly, if you believe you're categorizing your eyes as brown, that is a distinct, indivisible color, if you will, from dark brown or blue-green, right? So these are all discrete categorical values that can't simultaneously or fractally take on other values. Another thing that I want to talk about here as we're getting close to sort of wrapping up this lecture is, how is it that we present our data, right? Because in psychology, we use figures to convey a great deal of information about what our data set may look like, right? And when we do that, we want to be able to make sure that we're doing an ethical job at describing the shapes and features of those data. And so here I have a figure from your textbook, right? An example that shows changes in homicide rates in a city over a span of 4 years, right? And the reason why I bring this up is because remember that these figures are supposed to be a tool that we can use to get a quick and simple, but also importantly, accurate picture of the data. And we don't want them to be misleading because they can be misleading if they're not properly designed. So imagine a scenario in which we ran a statistical analysis on whether or not there was a difference between year, right? Whether or not there was a difference between year. And let's say that we didn't find a significant difference in homicide rates between years, right? That there was no difference between year 5 and 6, year 5 and 7, any other possible combination of these years. That even though this looks like indeed an increase, and it is technically, it is not a statistically significant increase. Now, if you didn't know anything about statistics, right, and somebody put this figure in front of you, and you looked at that, it might lead you to believe that there is a significant difference, there's a significant increase in homicide rates by year, because this looks just visually like a really big jump, right? But, if you note the y-axis, they're not lying here, but visually, this looks like a massive difference year by year. Perhaps a better way to display these data might be to increase the size of our y-axis, right? Here we're still showing that indeed it is increasing. But if you look at this, I think the first thing that sort of aesthetically should jump out is that, it's not increasing by much. And lo and behold, if we were to present a statistical analysis, that might confirm your instinct that indeed there is no significant difference between homicide rates over the years, right? So again, graphs can be misleading if they're not properly designed. That's something to keep in mind when you're creating a figure or when you're looking at one that is presented to you. And bonus points here. Some of you might be looking at this going, well, why is this being presented as a histogram, right? Surely this is discrete data, right? Murder rates, there's no fractal value of murder rates, right? But when you're presenting data over a time series like you have here, years are considered a time series, then you present that data in a histogram, right? So even though indeed murders are discrete value, right? It's discrete data. A city has 42 murders, not 42.7, right? Because you can't have really fractal values of murders. Whenever you're presenting data over time, whether that's years, minutes, hours, whatever, you should always present that data like a histogram here where the bars are touching. So just something to keep in mind. Also, another question on the homework is going to ask you to identify the shape of a distribution. And we're going to talk about a few of these shapes right here. The first one is one that we simply call the normal distribution, or a smooth curve, if you will. But really the appropriate thing is to call it a normal distribution. Typically you see it when we're talking about population data. I will say this. One of the things we're going to learn in this class is that if we have a large enough sample in any of our experiments, and we start to plot the results of those observations, they tend to start to fall under what we call a normal distribution. But anyway, one of these shapes is a normal curve. Some things to note about the normal curve is it's reasonably symmetrical. This one happens to be perfectly symmetrical, so if you fold it in the middle, both sides would match up. But if data is close to looking like a normal distribution without being perfectly symmetrical, we'd still probably refer to it as a normal distribution. And this sort of typically represents this idea that most people tend to fall near the average, right? We could say that this very middle line is the average or the mean. Most people tend to fall around the mean, with fewer people falling out to the extremes, right, to the tails of a distribution. So if you were to create a histogram or a polygon, and it looked something like this, right, really close to a normal distribution, then you would describe that data as being normal. Another shape is something that we call bimodal distribution. So if you were to generate a histogram, and that histogram had two really distinct peaks. Here they happen to be of equal size, but they don't have to be. One peak could be down here and one peak could be up here. But the point is, instead of having one major peak, like you see in a normal curve, maybe you have two distinct peaks. We call this a bimodal distribution. So in other words, it has points where you have sort of two clusters of scores kind of having a central peak as opposed to one, right? It doesn't have to be, again, symmetric, but sometimes it is. Here's an example where you might see a bimodal distribution, right? So imagine we have a class of 40 students, 20 are women, 20 are men, and imagine we measured the hair length for every one of our students. Well, again, there's always going to be exceptions. There's always variability, but we might figure, okay, if this was low inches to high inches, right? We might get a cluster of men in this range because they're typically, again, on average, going to have shorter hair, and women typically have longer hair. Again, there are always exceptions. And their cluster might be over here, right? So that would be an example of a bimodal distribution. We certainly wouldn't end up with a distribution that looks like this. The other two shapes relate to a concept that we call skewed distributions. So a skew can be, a distribution can be positively skewed if the scores pile up on the left side and then a tail goes off to the right. So remember, lowest value on the x-axis to the highest value, right? So in other words, there's a lot of sort of more of a peak of low scores and higher scores sort of tail off that are fewer and far between. A negatively skewed distribution is simply the opposite of that. So scores pile up on the right side of the distribution, on the higher range of the x values, and tail off towards the lower range of x values. And there's just one more little frequency distribution table that I want to talk about, and that's something that we call a stem and leaf plot. And there's also going to be a question in the homework about this. And so what you can do is the nice thing about a stem and leaf plot, and it works fine as long as you don't have too many scores. But the nice thing about a stem and leaf plot is it allows you to make a frequency distribution table and at the same time a histogram. So the first thing you need to do when you're making a stem and leaf plot is to establish the range of values, right? So here it looks like the lowest range of values that we have here. Oh, there's a 0. Okay, great. So somebody got a 0 on this sample of 24 exam scores. And what is our highest value? It looks like a 34. Okay. So I am going to have what we call a stem for every single 10-point range of values, right? That fall in the ones place, the 10s, the 20s, and in our case, since we top out at 34, the 30s range, right? So I'm going to create in horizontal, in vertical order from top to bottom, a 0, beneath that a 1, beneath that a 2, and beneath that a 3. And the 0 is going to represent all the values that occur, right, that we find in this distribution that occur in the ones place. The 1 is going to be associated with all the values in this data that occur in the tens place, so anything between 10 and 19. The 2 is going to correspond to anything in the 20s range, so any scores that are 20 to 29, and so on. But here's the deal. We're not just going to that 0 point, right, the first stem that we've created, and then just tabulating the number of values that occurred between 0 and 9. No. What we want to do is mark each individual value that occurs between 0 and 9 in the ones range, right? So we've got a 0, so we'd put a 0 in there. We've got a 1, right? How many ones do we have? We have 1, looks like we have 2 ones, so we put a 1 and then another 1. Do we have any 3s? No. Looks like we have a 4, right? So then we put a 4 in there, right? Looks like we have a 6, and so on. And every time I add one of these values, right, I want to make sure that it's equidistant so that when I get down to my next rows, right, the ones for the 10s values, the 20s and the 30s, I can put the corresponding values in those ranges directly underneath it. And what I'm going to end up doing is making a histogram. It's sort of weird to try and explain online. So what I want you to do is just pause the video, give it a try. And when you come back, you'll see the example. And if you didn't quite get it, I think you'll probably find it pretty easy. So go ahead and pause the video and give it a shot. All right, so this is what it looks like, right? Here's all of our original scores. I've created these stems over here like we talked about, and they're going down vertically. So 0, 1, 2, 3. Each one of these values, right, are values that occurred in our original data set from right here. And I'm just writing them down as they occur. So this 0 corresponds to this exact 0 in our data set. This 1 and this 1 correspond to this 1 and this 1 in the data set, and so on and so forth. Now when I get to the values in the tens range, this 0, what do you think it means? It means 10, right? Because we got one person got a 10 in our data, and there it is, right? So we denote that 10 in the tens range by putting a 0 here. This 1 doesn't mean 1, it means 11. This 3 doesn't mean 3, it means 13. And if we go back to our original data, you're going to note how one person got an 11, one person got a 13, and so on. And so what happens is when you end up filling this out, and note how I keep a nice sort of a perfect distance between each value, right? And I'm doing the same thing as I'm filling the values out in the lower rows. If I were to imagine sort of mentally rotating this so that it was horizontal, right? So that it was horizontal, it gives me a shape of the data, doesn't it? And what do you think the shape of that data is? What do you think it is? How would you describe that shape? Would we describe it as normal? I don't think so, right? I don't think we would also describe it as bimodal, right? There doesn't seem to be two distinct modes in this data. Looks like that data is skewed in some way, right? Out of all 4 of these figures that we've looked at, seems like these data in the histogram, right? These data in the histogram best match a positively skewed distribution, right? So that's how I would describe the shape of these data. Okay. So that's it for this chapter, right? So you've got everything you need to do at least the questions on your homework as they relate to this chapter. And if you find yourself sort of struggling with these, of course, you can always ask a question on the course website, or you can try to do the practice questions in the back of the chapter. The odd questions, the answers are in the back of the book, so that should be quite helpful. All right, good luck.